Good afternoon.
Good afternoon.
Good afternoon,
How are you?
Lois.
Hello, nice to meet you.
Nice to meet you too.
Okay, Amina. First, I have to congratulate you because Morocco will play against Portugal next Saturday.
Yes.
So be careful. Be careful.
Okay. We will see. We will see which.
I will keep the finger crossed for Morocco.
Oh yes, I'm not sure about that. Okay.
So I think that we can start the next session. Luis, would you like to introduce our next invited speaker?
Okay. I'm trying to see the program. I don't know where is the program. So perhaps you can invite.
So okay. So okay, I have the program. So I'll start our afternoon session. So good afternoon, everybody. Thank you very much for being here with us. And I would like to introduce our next invited speaker, who is Amina Tachafine from Calais, France. And the title of her presentation is Microscopic and Macroscopic Electrical Properties and Impedance Spectroscopy of Strontium Calcium Titanate Materials for Environmentally Friendly Monolithic Ceramic Capacitors. So please, Amina.
Thank you very much.
Screen.
Thank you very much, but I don't see my screen is okay. Thank you. Okay. Thank you very much, everybody. Hello, everyone. I'm Amina Tachafine from the Dynamics and Structure of Molecular Materials unit of the University of the Littoral Côte d'Opale in Calais, in the north of France. I don't know if you see. Yes, you see my my talk. Okay, that's okay. Up to move. Up. Yes. Okay. After an introduction, the first part of this talk will concern the synthesis and structure study of ceramics. The second part will deal with the macroscopic electrical characterizations of ceramics elaborated. Then I will present results of impedance spectroscopy at high temperature, and then I will conclude. In introduction, I will say that due to the rapid evolution of the development of telecommunication systems and advances in technologies of electronic miniaturization used in industries, an important need for high-frequency tunable components and multifunctional devices has arisen. Today, ceramic capacitors are one of the most widely used forms of capacitor used in electronic equipment. Ceramic capacitors are nowadays available in many versions, including leaded disc capacitors, lead disc ceramic capacitors, surface mount multi-layer ceramic capacitors, MLCCs, and so on. In this way, high-frequency systems for telecommunications have attracted great interest. In particular, tunable or reconfigurable frequency electronic devices such as resonators and high-frequency filters. Lead-based ferroelectric ceramics such as PZT have attracted worldwide research interest due to their high dielectric performance. However, its main disadvantage is the fact that it contains lead in regards with the European Directive restriction of hazardous substances, which prohibits different kinds of polluting materials. Accordingly, it is now necessary to implement materials without these prohibited substances and presenting low losses, high dielectric permittivity, and relatively stable properties in frequency and temperature. The aim of this study is the development of ferroelectric materials tunable by continuous voltage for radio frequency and microwave applications. The SRTI03 material, which is a simple perovskite lead-free material, displays a paraelectric behavior with a cubic symmetry at room temperature. Additionally, it presents low dielectric losses at high frequency. To improve the electrical properties of SRTI03 ceramics, it is possible to substitute A sites with another cation, such as Ca2+, Ba2+, Mg2+, and so on. Here we present the structural and dielectric study of SCT 0.4 ceramic, in which strontium is substituted by a high rate of calcium, which is 40%. This composition was chosen because of the low losses we had highlighted before. So this material could then have a great interest for the development of monolithic ceramic capacitors. This application is firmly recognized within the industry as a global leader in market and technology. Monolithic ceramic capacitors on circuits are used in extremely high temperature environments, such as in engine control units for vehicle engines and in various circuits used in sensors, for example. Concerning the ceramic synthesis, ceramic pellets with a diameter of 3 millimeters and a thickness of 3 millimeters were prepared by solid-state reaction method. Samples were prepared using stoichiometric proportions of carbonates and oxides. Appropriate quantities were weighed, thoroughly mixed and pestled, and subsequently calcined at 1250 degrees Celsius for 15 hours. The obtained powder was grinded and then pressed into pellets. The pellets were subsequently sintered at 1400 degrees Celsius. Here we have the XRD patterns of the ST and SCT powders at room temperature. All the peaks of the XRD diagrams were indexed to the pure perovskite phase. The peaks are intense and very narrow, showing a good crystallinity of the samples. ST materials shows a cubic symmetry. For SCT material, the observed peaks are characteristic of an orthorhombic phase or structure. All peaks shift to higher angles to theta with increase in calcium rate in SRTI03 material. This is due to the fact that the ionic radius of Ca2+ is smaller than that of Sr2+. Here we can see the SEM photographs of the ST and SCT ceramics. The microphotographs show a homogeneous microstructure and well-developed grain morphologies. We can see that the grain size increases with the substitution of calcium in SrTiO3 material. The average grain size is about 630 nanometers for ST and about 2 micrometers for SCT ceramics. The grain boundaries size is about, as we can see here, is about 40 nanometers. Now I will talk about dielectric measurements. Here we have the frequency dependence of the dielectric permittivity of ST and SCT ceramics from 100 Hertz to 1 gigahertz at room temperature. We can notice that strontium substitution by calcium decreases the dielectric permittivity. For SCT ceramics, epsilon prime shows a good stability all over the frequency range, whereas for ST ceramic, epsilon prime presents dispersion in low frequencies. SCT ceramic exhibit constant dielectric permittivity value, which is lower than the ST1, but definitely more stable all over the complete frequency range. This is an advantage for high frequency components. Sorry. Here we have the frequency dependence of tangent delta of ST and SCT ceramics from 100 Hertz to 1 gigahertz at room temperature. We can see that SCT could display loss tangent lower than 3.10 to minus 4 from 1 megahertz to 12 megahertz. And SCT tangent delta values does not exceed 6.10 to minus 2 at 1 gigahertz, while ST ceramic gives a minimum value tangent delta equals 0.05 from 500 kilohertz to 3 megahertz. Now, the quality factor is defined by Q equals 1 over tangent delta. Generally, for industrial applications, high quality factor ceramic capacitors must exhibit Q values higher than 1000 for frequencies up to 100 megahertz, or higher than 200 for frequencies ranging from 100 megahertz to 1 gigahertz. For our sample, we can see that SCT gives Q values higher than 2500 from 1 to 12 megahertz. Concerning the temperature dependence of the dielectric permittivity of SCT ceramic at different frequencies from 100 Hertz to 1 megahertz, we see that the dielectric permittivity is constant, is constant in temperature up to 250 degrees Celsius for all the frequencies, and up to 500 degrees Celsius for 1 megahertz. After that, epsilon prime quickly rises above these temperatures. This may be related to oxygen gaps that are heat activated in the material. If we expand the scales, we see that the dielectric permittivity presents a slight decrease from room temperature to 150 degrees Celsius for all the frequencies, and no phase transition is observed. The SCT gives a relative variation of 15% up to 150 degrees. The stability of the dielectric permittivity with respect to temperature is very interesting and shows that SCT could be used in ceramics capacitors applied to high temperature environments such as the automotive or military field, for example. Concerning the loss tangent, it remains smaller than 0.05 up to 200 degrees Celsius from 100 Hertz to 1 megahertz. The minimum tangent value obtained for the SCT ceramic is 8.92 - 100 kilohertz and 100 degrees. It is certain that these low losses values are very interesting for the development of high quality lead-free ceramic capacitors for applications requiring high temperatures. Beyond 300 degrees Celsius, the loss tangent increases sharply. This may be due to the increase of dielectric losses at high temperature in the material. Sorry. Here we have presented the imaginary part of the complex impedance of the SCT ceramic as a function of frequency at different temperatures from 300 degrees to 500 degrees Celsius. We can notice that there are two thermally activated peaks clearly visible from 450 degrees. Indeed, as it can be seen here at 490 degrees, the first peak is located at low frequencies and is attributed to grain boundaries, and the second peak located at high frequency is attributed to the ceramic grains. Both peaks are visible on the evolution of minus z second, but only the peak attributed to the grains is visible on the evolution of the imaginary part of the dielectric modulus m second. Here we have plotted Nyquist diagrams. As you know, the Nyquist plots between the real and imaginary part of impedance is used to analyze the AC conduction mechanism in any material. These graphs usually appear in the form of semicircle, and each semicircle is a manifestation of unique relaxation process. The appearance of a perfect semicircle with its center lying on the abscissa in any Nyquist plot shows the bi-type relaxation mechanism. A depressed semicircle as we can see for our plots, shows a non-Debye type behavior demonstrating the presence of a constant phase element or CPE. On the Nyquist plots here at t equals 490 degrees, the two peaks are clearly visible, one in low frequencies and the other in high frequencies. Nyquist plots at 490 degrees highlights two relaxation mechanisms. Since we clearly see two circle arcs corresponding respectively to grains and grains at high frequencies and grain boundaries at low frequencies, each arc can be modelized by an equivalent circuit, an equivalent electric circuit containing a resistance R in parallel with a constant phase element CPU, represented by the Q quantity and the dimensionless parameter N. Both circuits are in series. We have adjusted the Nyquist diagrams using the Alchemia analytical software. This software gives us for every arc the values of R, Q, C, and N elements for the grains and grain boundaries. Here we have plotted the resistances of grains and grain boundaries. As we can see, they decrease with the temperature increase, showing an activated thermal conduction mechanism. We can see an Arrhenius type evolution with a change of slope at 460 degrees, more pronounced for grains resistance, which indicates that there are two mechanisms of charge carrier conduction. Here we have plotted the apparent grain and grain boundaries capacitance determined from the relaxation frequencies and resistances of the grains and grain boundaries. Sorry. Okay. The apparent grain boundaries capacitance is 20 times higher than that of the grains, and both do not seem to vary with temperature. Here we have plotted the relaxation times of grains and grain boundaries. They are calculated from resistances and apparent capacitances. They have a similar variation in temperature to those of resistances, since apparent capacitance are constant, as seen on the previous slide. They also show an Arrhenius type evolution with the change of slope at 460 degrees, indicating a modification in the conduction mechanism of the charge carriers in the grains. Sorry. In the equivalent circuit model, constant phase element for grain boundaries has been inserted instead of capacitor due to non-ideal behavior of capacitance. We have also plotted the constant phase elements representative for grains QG and grain boundaries QGB in temperature. We notice that QGB is about 100 times higher than QG. Indeed, the grain boundaries act as trap centers for charge carriers, so they are more insulating than grains. We also notice the change here of slope, which indicates a change of conduction mechanism from 460 degrees in both grains and grain boundaries. The parameter n estimates the deviation from ideal Debye behavior, with n equals 1 to non-Debye type behavior, which is due to heterogeneities and defects in the material, causing distribution in relaxation times. The n parameter values lies between 0 and 1, showing the deviation from a pure resistor behavior to a pure capacitance nature. On curves, we can see that for T lower than 460 degrees, Ng is near to 1, indicating that the grains are well crystallized. For T higher than 460 degrees, Ng decreases. This is probably due to oxygen vacancies increase. And for grain boundaries, the N parameter is far from 1, showing the presence of defects in grain boundaries. We also found on the evolution of the N parameters the discontinuity around 460 degrees, showing a change of conduction mechanism in grains and grain boundaries for T higher than 460 degrees Celsius. We show here the evolutions of the inverse of resistances of grains, grain boundaries, and SCT ceramic. The resistance of the ceramic is obtained by adding the resistances of grains and grain boundaries. These evolutions as a function of the inverse of temperature are of Arrhenius type. We notice that the resistance of the ceramic is very close to that of the grain boundaries. Therefore, the activation energy of the ceramic and that of the grain boundaries are close. Two values of activation energy were found for the grains. 1.5 electron volt between 40 and 40, between 400 and 460 degrees, corresponding to oxygen vacancies jumps, and 0.68 electron volt between 460 degrees and 510 degrees Celsius, corresponding to polarons. Now, the DC conductivity of the ceramic is calculated from the resistance, as you can see the formula, is calculated from the resistance, thickness, and surface area of the ceramic. We have plotted here, we have plotted it as a function of the inverse of the temperature, as well as the AC conductivity measured at 100 Hertz. We note a good agreement between the two conductivities, which validates the calculations of the ISyDMA’ software. We then deduced from software for ISyDMA’ software calculations the values of the DC conductivities of grains and grain boundaries, because they are inversely proportional to the resistances calculated by the software. We can notice that grains conductivity is very large compared to that of the grain boundaries, although the ratio decreases when the temperature increases beyond 440 degrees. We have calculated the potential barrier of grain boundaries. It can be calculated from the ratio of the continuous conductivities of grains and grain boundaries. It shows a little variation, about 6%, with a maximum around 400 and 460 degrees. Nonetheless, it is now possible from the potential barrier of grain boundaries to compute the ratio of oxygen vacancies concentrations in grains and grain boundaries. And if we represent on the same graph the evolutions of the ratio of DC conductivities of grains and grain boundaries, and the ratio of oxygen vacancies concentrations, we notice to a first approximation that the two curves look the same. This allows us to say that at these temperatures, continuous conductivity in the ceramics grains and grain boundaries is essentially due to the diffusion by jumps of oxygen vacancies. Concerning the real and imaginary parts of the ceramics complex impedance, they are calculated from those of grains and grain boundaries according this formula, this further following mathematical formulas, in which the different elements are calculated by ISyDMA software. We have represented here the frequency evolution of the imaginary part of the calculated complex impedance of the ceramic grains and grain boundaries, as well as the imaginary part of the measured complex impedance of the ceramic. These evolutions show a good agreement between calculated and measured values of the ceramic impedance, as well as grain boundaries contributions in low and medium frequencies, and grain boundaries contribution in high frequency. Now, the distribution function of relaxation time, or DFRT, gamma of tau, of an electrical RC parallel circuit is given by this rigorous analytical formula as a function of tau, tau 0 and n, with tau equals 1 over 2 pf, where f is the measurement frequency. Tau 0 is the RC time constant, and n the dimensionless parameter. We show here the R gamma evolution, where R and gamma are respectively the resistance and the DFRT of the ceramic, obtained by adding DFRT of grains and grain boundaries. The distribution of relaxation times in grains is spread over 1 decade, and is much lower than that in grain boundaries, which is spread over 3 decades. This may be related to the fact that the relaxation times are more distributed in grain boundaries than in grains. The distribution function is derived from the impedance through solving this Friedlum integral of the second kind. By comparing frequency evolutions of the imaginary part of the complex impedance and of the R gamma, we show a good agreement on relaxation frequencies in grains and grain boundaries, given by minus Z second measurement and R gamma calculations, and also on maximum peaks on amplitudes, maximum peaks amplitudes. Finally, we present here frequency evolutions of minus Z second, tangent delta, M second, and R gamma of the ceramic at 490 degrees Celsius. They are normalized to 1. The evolution of minus Z second and R gamma obtained from impedance measurements clearly show grains contributions at high frequency and ground here and grain boundaries ones at low and medium frequencies with good agreement in relaxation frequencies and maximum peak amplitudes, while the evolutions of tangent delta and M obtained from dielectric measurements show only grains contributions at high frequencies. Indeed, grain boundaries effects are not visible because masked by low frequencies effects such as charge accumulation, polarization at electrodes, and so on. In conclusion, we can say that SCT ceramic with 40% of calcium is a good candidate for the development of monolithic ceramic capacitors dedicated to high-frequency lead-free components and or to extremely high temperature environments due to the stability of its dielectric permittivity and its low dielectric losses over a wide range of temperature and frequency. Impedance spectroscopy measurements at high temperature and fitting using Alchemia software enabled us to study conduction mechanisms in grains and grain boundaries, as well as their electrical properties and contribution to dielectric ceramic behavior. It only remains me to thank you for your attention and to invite you to visit our laboratory and your beautiful region in France. Thank you very much.
Thank you very much, Amina, and thank you for keeping the time perfectly. So we still ask 1 or 2 questions.
Anna, did you see any questions in the chat or not?
No, there are no questions.
Okay, so nothing perhaps I can make a question to your opinion, Amina. You show that epsilon prime of ST is really higher than the epsilon prime of SCT.
Yes. Okay? Yes.
But you say that SCT is more stable.
Yes.
But actually, epsilon prime for ST is really higher. So do you think it's more important the stability or the value of epsilon prime?
Of course, the stability. The stability is more important because you can use the material on a long range of frequency.
Okay.
It's more important.
Okay. It was interesting to see this calculus of n, this exponent that you use in constant phase element. It is close to 1 in the grain, so that means that it's a Debye relaxation. Is this expected to you? It is normal because Debye relaxation are not so common.
I didn't hear the end of your phrase.
The Debye relaxation are not so common in the materials, and in the US, the relaxation for the grain because n, this exponent that you have, the CPA element is close to 1.
Yes, it's close to 1. So grains and are well crystallized, and in grain boundaries, n is far from 1 because of defects in grain boundaries.
Okay, thank you, Amina, and good luck for Saturday.
Good luck, you too.
Thank you. So
Thank you
now,
very much.
thank you everybody. So I have to split to the room 2. So have a nice afternoon. Thank you.
Thank you.
Thank you.